So what's the goal for today? We're going to talk about characteristic polynomials. And I think we've mentioned this before, and if you haven't mentioned it before, you're familiar with characteristic polynomials from linear algebra. So, in general, given a matrix M, and this is any matrix right now, just a square matrix, and we can look at the polynomial, we'll call it P of X. Sometimes people put subscripts, maybe just to specify which matrix it is if it's ambiguous. And this is the determinant of xi minus m. Okay, so that's the characteristic polynomial of a matrix. And what do we know about this polynomial? Well, what do we know? Why do we care about this polynomial? Yeah. So the key, why we bring this up, is that the roots of our polynomial, p of x, these are our eigenvalues, including multiplicity. And now, of course, for our matrix that we consider, in fact, all our matrices that we consider, we're keeping things symmetric because, after all, we like to keep it real in this class. But one of the things that means is that we have a nice full set of eigenvectors. Not everything has that. Sometimes you come short in eigenvectors, but you always have your eigenvalues. So that's good to know. So it's good to know, well, what is the characteristic polynomial? How can you compute it? And can you learn things about the graph by studying the characteristic polynomial? So that's our goal. That's our goal. Okay, so probably we should begin. We're going to talk about a determinant. We should remind ourselves how to take a determinant of a matrix. So the definition of determinant. So I'll say of a matrix B. Does anybody know the formal definition? There are multiple. Yes, very good. The sum definition. So over all permutations in Sn, your symmetric group of n elements. So I'm assuming here E is an n by n matrix. And so it needs to be square to talk about determinant. All right. So we're in over all determinants. How do you compute the determinant of a matrix? Do you remember the definitions? Oh, good. You got the hard part. Sine of sigma. A lot of people are like, good. And what's the rest of it?
And then you have B sub 1 of sigma 1,
right.
B sub 2 sigma
2. B2 sigma 2,
B,
all the way down to B and sigma n. Now, if you're trying to think about what's going on here, what you're doing is we're really taking, in our matrix here, we're taking a collection of entries. One entry in each row and one entry in each column. And we're doing that in all possible ways. And I think these are sometimes called the traces. So we usually talk about the trace as the main diagonal, but you can run over all possible. And so we're running over all possible ways we can combine these together. And then we have the sine of sigma. And this is, it's either plus or minus 1. And how do you determine that? Well, it depends on the number of pairwise transpositions to get to the identity. While we're here, there's a related idea to the determinant called the permanent. And what's the difference? You still sum over all the entries, and you still have the B1 sigma 1 to Bn sigma n. But what goes here? Yeah, just 1. It's yeah. So you don't need the sign. Now, when you're first starting off in the subject, you say, this seems easier, the permanent. You don't have this pesky sign to keep track of. But once you get a little bit further, which one is actually easier to work with? Determinant is a lot easier to work with, in that the determinant can be computed quickly, and the permanent is kind of hopeless. Now, you can do things like cofactor expansion for the permanent, but why does this sign help? And one of the things that you get as a consequence of the sign, you get things such as if you add a multiple of one row to another, then you don't change the value of the determinant. So you can do row operations to simplify your matrix first, and then take the determinant. All right, now here we've talked about very general things. Let's actually talk about our setting. So for now, we're going to assume that the matrix we care about is A, our adjacency matrix for our graph. And we want to understand, what does our characteristic polynomial look like? So PA of x. Well, of course, we can start in the same place. Sum sigma and Sn, sine of sigma, and we'll write A1 sigma 1 dot 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 An sigma n. Now, that doesn't really do much for us. We'd really, really like to get to a point and say, can we understand this in a much simpler way? All right, so let's help ourselves. Oh, wait, no, I got to be careful here. That's not quite PA of x. Let me cancel that. That's okay. We can simplify this. Well, let's write what we want. So this is the determinant of xi minus a. So maybe it's helpful to have an example. Let's use the PA graph, not because it's the best example, but because it's small enough that we can probably write it down without going crazy. That's a good measurement on whether or not you want to do it. So we assign some labeling here. So if I look at the adjacency matrix, well, it has a nice structure, and we can write it down relatively quickly. So here's our adjacency matrix, and we want to look at xi minus a. And all right, so what does that look like? Xi minus a versus what x looks like.
That one's along the diagonal and all of your ones are going to be.
So yeah, off diagonal we'll have negatives, and diagonal will be x's.
Yeah.
So x minus 1 minus 1 minus 1 minus 1 minus 1 minus 1 0. Oh, sorry, x minus 1 0 minus 1 0 x 0 0 x. All right, so that's our determinant. Okay, so we have to think about what's going on, and so we'll look at some possibilities. Now, notice that when we multiply these things, if one of my entries is 0, what's going to happen? You get 0, right? So the only contributions, I'm only looking for, I call them traces. I think they're probably transversal, it's just a technical term. This is what happens when you don't teach linear algebra for 5 years. You lose these definitions. All right, so when we're thinking about this, we can say, okay, just focus on the transversals which don't have a 0. All right. Well, okay, so let's see. What would they look like? Well, there's some really silly ones. Namely, I could just take the diagonal, main diagonal, which is all x's. All right. Well, let's see if we can do a not silly one. And This will get me in trouble here as I try to use more and more colors. But, all right. So let's say I pick here, and here, and here, and here. We can say that there's possibly some x's and some negative ones. And we're going to ignore everything with the zeros. So we have x's and minus 1. So the x's, well, that just means you have the vertices. So here it says vertex 3 and vertex 4 aren't used. So it's sort of saying, okay, vertex 3 and vertex 4 aren't used. But what's happening here with the minus ones? Well, you have the 1, 2 entry and the 2, 1 entry. And so you can think of it as the 1, 2 entry, you can think of it as 1 to 2, and the 2, 1 entry as 2 to 1. Now you might say, why are you drawing it with arrows? And we'll get to that in just a moment. So that's one example. All right. Let's try another example. Can I still keep using the same matrix, or should I start with a fresh one? It's about to get messy. One more layer in. All right. Okay, so we're going to do circles now. Circles, circles, and circles. It's the circle of life. Okay. Now, what do we have here? Well, we have a single vertex that's not being used, so that's 4. And then we have 1, 2, 2 to 3, 3 to 1. Well, this is, you have the right idea. So one way you can think about an undirected graph is you can say, actually, it's a directed graph where we just put back and forth on each edge. And so that's our paw. It's just both directions on each edge. And well, okay, so what's happening? You were mentioning cycles. Well, think about the idea of a transversal. We have to have something on each row and something on each column. Now, if I have something, okay, so if I have an entry here in the 1, 2, well, can I also pick the x in, say, row 2? No. So if I pick an entry off the diagonal, I can't pick an x in that row, and I can't pick an x in that column. But I can say, okay, this entry is an edge. It goes 1 to 2. So when I come to 2, I say, well, I can't stay at 2, because that would be the diagonal. So when I look at row 2, I'm looking for a minus 1 somewhere, which is telling me where to move. There's exactly 1 minus 1 I'm going to use in that row. Because each row is either a minus 1 or an x, or I didn't even bother to look at it. And so what's happening is when you look at the minus 1s, if you ever don't stay at that vertex, you're always going to come in and go out. So 1 in and 1 out. And if you think about what kind of directed graphs have the property that you have one thing coming in and one thing going out at each vertex. Well, we'll think of an unused vertex. We can even think about adding loops. Okay, you said cycle. Can you think a little bit more? In other words, I like the first 5 letters.
Cyclic?
Well, no.
That's 4 letters.
Just one more letter to cycle.
Cycles.
Cycles. Cycles. Yes. And so you could have multiple cycles. So as an example, you could do 1 down to 4, 4 back to 1, and you could have 3 to 2, and 2 to 3. So those would be 2 disjoint cycles and not one cycle. And so there's sort of the great aha moment, as we often have. We have these aha moments when we're looking at things and we're like, aha. And the aha is to say cycle decompositions. When I'm looking at what contributes non-negative terms, I look at the corresponding edges in this directed version, it matches with cycle decompositions. Okay, so we're going to think about this in terms of a sum of cycle decompositions of A. Cycle decompositions of our graph G. So our graph G. Now, we should probably define what a cycle decomposition is. And so a cycle decomposition of G is I want to be careful here. Is a way to decompose the graph into vertex disjoint cycles where each vertex is in one cycle. And then there's just one other thing we should say. We're going to consider a single vertex. I'm still on the page. Single vertex is going to be a cycle of length 1. An edge is a cycle of length 2. So we want to look at all these different cycle decompositions. So the goal is to say, we're going to sum over the cycle decompositions, and we're going to say there's something that goes in here. So for each cycle decomposition, there's a contribution. So this will give us a combinatorial way to compute the characteristic polynomial. Well, all right, we're filling up the page here, so let me move this up. Oh boy, I bled a lot on that page. That's all right. We'll just put that aside for a second. Let's talk about the PAW graph again. And I just want to talk about what are the different cycle decompositions of the PAW graph. How many are there? So you can start thinking about that. I'll draw a couple of copies of the PAW graph. Okay. What are some cycle decompositions that you can see?
Every vertex by itself.
Okay, every vertex by itself. Great.
Vertices swapping and the other two staying.
So, like, what do you mean? What's an example?
The top two swapping places and the bottom two staying inside.
Okay, so an edge, and then 2, and then we'll do it for each edge. Okay.
The 3 cycle and the bottom vertex by itself.
Okay.
For each of the valid modules for, I think the first one and the last of those 4, you can have an edge and another edge. Yeah, which is the one that should go between these. Yeah. Top edge and bottom edge, yeah.
Okay. All right. Any others? I'm not claiming that this is the correct number.
Can you just go through the whole graph?
Can you? Well, the problem is, would I be a cycle?
Should I not be thinking of directed graphs anymore?
The only cycle that can
But directed graphs still, you can talk about cycles. For cycles, you have one in, one out. So if I were to say come,
There'd be three. Oh,
doom, doom,
Okay, good.
I'd have multiple ins and outs.
Yeah, it has to be a Hamilton.
Do we have to double count the one you just did for both ways we rotate around?
Oh, wow, you are ahead of the game, my friend. Yes, yes, you are correct. We do have to do that.
Oh, the cycle? Yeah.
Yeah, well, because remember, underlying all of this, when we really talk about cycle decompositions, and we're thinking about the matrix, well, because we have ordered, the 1, 2 entry versus the 2, 1 entry, the question is, which way do you move in your cycle? So here, we don't specify direction, so you do have to take that into account.
And on the matrix, it'll be a matter of
Yeah. Okay, so let's think about cycle decompositions. So contribution from a cycle decompositions. And we'll simplify things. Let's start with a vertex. Suppose we have a vertex. And remember that we're doing this, the determinant xi minus a. What's the contribution that a vertex is contributing?
just a vertex will contribute x.
Correct. Because the vertex says you're on the diagonal. So that's x. What's the contribution from an edge?
Just an edge
Just one single edge.
should be 1. Because they're swapping places.
Okay, so an edge, I'll use a green here for the edge. We have 2 minus 1s,
And multiplying the entries.
and we multiply the entries, which gives us a, yes, and of course you're saying 1, which is the right answer. But somehow I'm not writing that down.
Yeah.
It's like, what? Write it down, Steve, write it down. But okay, so be careful here. Let's pull back.
Maybe like negative 1.
Remember, we're looking at these pieces, but think about what happens here. What would be the sign? What would be the contribution? So transposition basically says you're swapping vertices. And so what will happen is if I have an edge, I'll have a single transposition I'll need to make.
Right.
So,
So the sign is negative 1.
right. So we'll get a minus 1 from the sign part, contribution, and then a minus 1 times minus 1 because we'll have those edges. So the net contribution is negative 1. Okay.
X has a sign positive 1 because it's zero transposition.
All right.
Okay.
Yes. Now we're going to go with a cycle of length greater than or equal to 3. All right. What's the contribution going to be? And I already know you're anticipating, wait, Steve, you have to do odd versus even. Okay, we'll do odd versus even, no problem.
Length or odd computation?
Well,
Or are those the same? Because I haven't decided yet.
An odd cycle should be a positive one. Even should be a
I agree.
I
So
also
the sign of an odd is positive.
okay, so the sign of an odd will be a positive 1, so this is our sign part. I agree there.
Even should be negative.
So this is length of
Okay, the even will be a negative 1 for the sign part. Okay, what about the product of the edges? It'll be a minus 1 to an odd number. Here it'll be minus 1 to an even number. Anything else? I know there's not a lot of space there, but there's some. We could maybe squeeze in one little tiny piece. A 2. Why the 2? Because remember, we could have gone around that cycle in 2 different ways. So what's happening is when we talk about the cycle decomposition, if we come back to this page, when we sum over all the permutations, it's not that every permutation is a cycle decomposition. Cycle decompositions could correspond to multiple permutations depending upon how you choose to orient ways around the cycle. Now for an edge, there's really no choice because you only have one way to go back and forth between 2 vertices. But for any cycle of length 3 or higher, there is a choice, one of 2 choices. And so be careful here. It's not like there's a matching 1-to-1. It's just, so one cycle decomposition will be many possible sigmas. All right. Can we clean this up? Yeah. Negative 2. So we can put this all together and we say, okay, for a cycle decomposition, the total contribution, we have x to the number of vertices. My pen didn't want to write vertices. Okay. We have minus 1 to the number of cycles of length greater than or equal to 2. Because a 2 cycle contributes a minus. A cycle of length 3 or higher contributes a minus.
Okay.
And then we have 2 to the number of cycles of length greater than or equal to 3. So, in particular, that's the contribution from one single cycle decomposition. Sum over all cycle decompositions, and what will happen is that you will recover every possible, whoops, I pointed down here, I should be pointing here. You'll have recovered every possible one of these terms. So the punchline is that the characteristic polynomial for our adjacency matrix, which is this determinant of xi minus a, is the sum over all cycle decompositions. And then we do x to the number of vertices. We can do minus 1 to the number of cycles, where we just understand cycles include cycles of length 2, and 2 to the number of, I'll call it long cycles. You know, a long cycle it's a cycle whose length is close to infinity, like 3 or higher. You know, because there's, of course, a mathematician is giving a talk and says, pick a number close to infinity, like 3. Well, 3 is just as close as any other number. So, okay, I left myself some space. Let's compute the contribution from each one of these. So for this first one, what's the contribution?
To the 4th.
X to the 4th, because everything's an x. For the next 4, they all have the same structure, right? Because we just care about, like how many cycles do we have? They all have the same number of cycles. They all have one cycle of length 2 and 2 cycles of length 1 vertices. So what does this first one contribute? Negative x squared. And then these will contribute negative x squared for a while here. Okay, how about this term? It'll contribute 1. Well, because you have a minus 1
Exactly.
and a minus 1. So that's a 1. And how about this part?
2x.
Negative 2x. Because you have a negative 2 from that cycle
Oh, right, greater than
and an x from that cycle. And you put this all together and you say, okay, so this characteristic polynomial, x to the fourth minus 4x squared minus 2x plus 1. So we found the characteristic polynomial for the Poisson graph. And we did it in a combinatorial way by looking at all the possible ways that we could have written this out. All right, good. Well, should we try some other graphs?
Yes.
All right. Well, let's try. I don't know if we've given this an official name. We probably have said this before. The star graph. Can we find the characteristic polynomial for this graph? And so let's say we have, how many leaves do you want to put here? N leaves? Okay, I agree. N leaves.
Each one is going to have either no cycles or
Okay.
one cycle because they'll take up the middle vertex.
Right. So there's only 2 cycle decompositions. So one of them looks like this. Now when I say 2 cycle decompositions up to symmetry. And then the other one, and then of course I probably should have picked a number that's easy to count here. But the other one will have an edge and isolated vertices. And then this will happen n times. So, what's the characteristic polynomial? X to the n?
Well, x to the n plus
Plus
1. X to the n plus 1.
Plus 1?
And
Okay.
leaves. And then n times. I want it to be n times.
Okay, there's n of them.
Should be n times.
It should be
Negative x to the n minus 1.
x to the n minus 1. And there we go. All right, well that one was easy.
No.
Yes. Actually, we can make a quick comment here. A star is a special case of a tree. Now, what do cycle decompositions look like in trees? Ah, what's a matching?
It's like a 2 coordinates the edges.
It's a 1 factor.
Okay,
No.
equals a 1 factor. Okay,
That's wrong. That's wrong.
what's a 1 factor?
A matching is a set of pairwise disjoint edges.
Yeah, so it's a set of pairwise disjoint edges. Now, we do not need to have all edges involved. So we can use just some. So we're not trying to like maximize a pairwise disjoint edges. So should we do some paths? There's a fun thing that happens with paths. Okay.
Could you cross out that 1 factor? Thank you. No, nobody's confused.
All right.
No, 1 factor is oh, it might be a spelling.
I think 1 factor might be okay. I think it depends on the definition. I don't know if 1 factors are required to have every vertex involved. Well, not everything Doug West says. No. Of course. If you're talking graph theory and you're talking like, I read the hollow text today, then you read Doug West. And so, okay. Well, a single vertex counts as a path. Okay, so what's this characteristic polynomial? X. All right.
X squared minus
Yeah, x squared minus 1, because you have nothing gets there, or just the edge. And you can check to see if this is true, because what are the roots of x squared minus 1? Yeah, so plus minus 1. This is k2. And we know how to compute the eigenvalues of k anything. So 1 is an eigenvalue because it's one regular, and then the other eigenvalues are all minus 1. You know, all one of them are minus 1. All right. So now we have to think a little bit about this next one.
This one's a star.
It is a star. Okay, so maybe we don't have to think very hard.
Yeah. So n equal to 2, so this will be x cubed minus 2x.
X cubed minus 2x. Yep. All right.
Now we have to start.
Now, okay. At some point today, we were going to have to think. So it's inevitable that sooner or later one must think. So, okay, so we have x to the 4th. No matching. No edges in our matching. Now, if there's one edge in our matching, how many ways are there to have one edge? 3. And it'll be 3x to what power? Well, it'll be x squared. Because one edge will use up 2 vertices, so that means we have 2 unused vertices. Okay, can we have 2 disjoint edges? In one way. So 2 disjoint edges, so that's minus 1 squared, which makes a plus. It'll be, what will be the power of x? So it'll be 1, x to the 0.
Yes.
All right, x to the 4th minus 3x squared plus 1. Now, one more, and then we'll be like, ah! Or maybe we won't, I don't know. Perhaps you've already seen this. But 5. Okay, first off, it's x to the 5th. Now you might say, you notice like all the powers are odd and odd or even. Well, that's just, it's a consequence of being bipartite. And, okay, so x to the 5th. How many ways are there to have one single edge in our matching? 4. So 4x cubed. How many ways to have 2 edges? 1, 2, 3.
No, you're right. 3.
And minus or plus?
2 edges.
Plus.
Should we do one more?
Why are there only 3 computers?
Well, because we can't have 2 edges next to each other,
Oh, right.
Yeah.
and so they have to be a little bit far away.
It's really easy to say you have these 2 or these 2, but no, also the ones that are more than one of them.
All right. We'll fill up a little bit of time here.
Okay, x to the 6th.
Okay, x to the 6.
And then this is going to be what I propose, minus 5x to the 4th plus.
So you can just start here. You have 1, 2, 3, 4, 5, 6. Yes? All right. Start here. So hold this one. 1, 2, 3. Now hold that one. 1, 2. Hold that one, 1. So 3 plus 2 plus 1. So 6x squared. And is there any more?
Yes.
So is it possible to have 3 disjoint?
Yes.
Yes. One possible way.
No x.
All right. So, is anybody recognizing these? Is this like feeling really familiar? And if not, what happens if you plug in I and then take the absolute value? So plug in I, take the absolute value, and the first one, what do you get? 1. The second one, you get
What is I?
I squared equals negative 1.
Oh, okay.
Here,
The absolute value.
3.
Oh, okay. No.
3. Here,
4.
1
4,
plus 3 plus 1, 5.
Is it Fibonacci numbers?
8,
No.
13.
Yeah,
Do you recognize them?
incredible, yeah.
Yeah, they're Fibonacci numbers. Now you might say, what? You're messing with me. But actually, we can explain it pretty quickly.
Does that suggest that the graph with 0 vertices has also an eigenvalue of 1?
Yeah.
Well, that's an interesting question. So, what's the determinant of the empty matrix? Is it?
Yes. I want it to be 1. I want that.
No, I agree with you. So the thing is,
By determination.
I agree that the question is, do you think of a determinant as a sum of a product? Or do you think of it as like a product of something? Because when I think of it as a sum of a product, it's an empty sum. And my convention says empty sum should be zeros. But if it was thought of as a product, an empty product is 1. And so I don't know. We could, well, certainly we want it to be 1 based on this.
I'm going to offer an alternative thing here.
Okay.
Vacuously, it has every single real number as an eigenvalue. So its characteristic polynomial is the infinite product of x minus like y for every real value.
I'm not sure if that's a true statement.
So it's, I mean, if you think of a determinant as the product of the eigenvalues, then the determinant is the product of the set, which is 1. If you determinant is the sum that we said earlier today.
Right.
And also, I want determinant to have like some direct sum property. That if I take the direct sum of 2 matrices, I want the determinant to multiply. And so if I take an empty graph, it's going to have to be 1 for it to be done.
I think it's reasonable to say that a determinant of an empty thing is 1. Sure.
I think that's the best
I mean,
yeah.
usually, how do we define vacuous things? It's what's ever convenient.
Yes.
You know. Okay. So for people who are experts in Fibonacci numbers, what's a popular interpretation of Fibonacci numbers?
The golden ratio?
Well, there's that. It turns out there's a nice connection to the Fibonacci numbers in the golden ratio, but there's a combinatorial interpretation. Some people talk about it in terms of bricks, and they talk about it in terms of like horizontal and vertical bricks, but you can cut it in half. And then what kind of bricks do you have? So in other words, like top half, bottom half. Well, you have horizontal bricks that are length 2, and then you have single bricks, which are 1 by 1s. So it's 2 by 1s and 1 by 1s. So you can think of my bricks are something like, I have a brick of length 2, some single bricks here, and a brick of length 2. And then you go over that in all possible ways. And then it turns out that when you put I in, it just makes everything have the same, orients everything the right way so that your plus minuses don't matter. So it gets rid of the plus minus action. And so really what's happening, there's something called the Fibonacci, which are the Fibonacci polynomials. And you're seeing those entries these are the Fibonaccials, but they threw in some signs and they threw in some higher powers of x's. But that's actually what's going on. And so, all right. Looking at the time, this is a great place for us to stop.